Hello students, and welcome to section 6-7, Roots and Zeros. Synthetic types of roots. The following statements are equivalent for any polynomial function f of x. C is a zero of the polynomial function f of x. C is a root or solution of the polynomial equation f of x equals 0. X minus c is a factor of the polynomial function f of x. And if c is real, then c comma 0 is an intercept, technically an x-intercept, of the graph of f of x. The fundamental theorem of algebra states that if every polynomial equation with degree greater than 0 has at least one root in the set of complex numbers, we'll be anticipating when you see a function, you'll see that the number of zeros should match the degree, even if those zeros are complex. And if you recall, complex numbers of the form a plus bi, such that b is any real number, that's what this notation means, b is any real number. A plus bi speaks to a complex number form of which b can be a number like 1, or it could be -1, +1, or 0. It could be any number, technically, any real. If it is in fact 0, then A is, well, on its own, just a real number solution. So overall, you will see an x-intercept or a root, same thing, defined on the graph. A corollary to the fundamental theorem of algebra is that a polynomial equation of the form p of x equals 0 of degree n with complex coefficients has exactly n roots. In the set of, again, complex numbers, included repeated roots. We've talked about repeated roots as a graph that touches the x-axis versus crossing the x-axis. So repeated roots bounce or touch, as we described earlier. We are not going to deal with Descartes' rule of signs, so we won't see those examples at all. However, example 1, it says solve the equation 6x cubed plus 3x equals 0 and state the number and type of roots. So we can factor this particular cubic. There is a GCF of 3x, as you can see. When you factor out a GCF of 3x, you're left with then 2x squared plus 1. You can set this equal to 0, as you can see, and end up there with x equals 0. And you can set this equal to 0. When you set that equal to 0, you get this equation, subtract 1, divide by 2, and then take the square root of both sides, wherein you'll end up with I, because the square root of a negative number, as we remember, is just that, I, partly. In this case, we're also taking the square root of a half, which simplifies as root 2 over 2. Make sure you rationalize your denominator. In the end, there are roots that match the degree. The degree is 3, so it has one real root of 0, but it also has two imaginary roots, of which you see here, plus or minus I root 2 over 2. Now that can also and should also really be written as the square root of 2 over 2i. Typically we like to put the I after the b value. Again, a plus bi in the context of a complex number. Now what I've done here is I've pulled in a equation on Desmos. I've already graphed here, as you can see, and the graph does highlight, as you can see, the x-intercept, of which is the real root. The two imaginary roots you will not see on the graph. However, to count all three, number 1, the real 0 you can see, and the two imaginaries that you cannot, to equal in total the third degree function. As we continue, we'll take a look at some of these exercises that I've done. It says solve each equation, state the number and type of roots. So x squared plus 4x minus 21 equals 0. This is a factorable quadratic, of which you can see x plus 7, x minus 3. Foiling does in fact prove that out. 7 minus 3 is 4. 7 times -3 is -21. One root is -7. The other root is 3, and they are real. You will see that on the graph. So two real roots. Number 2, this cubic has a GCF of 2x, which you're left then with x squared minus 25 upon factoring. Notice it's still equal to 0. You can set 2x equal to 0, and you get x equals 0. You can factor x squared minus 25, of course, to get x plus 5, and x minus 5. You can set that equal to 0 to get negative 5, and this, of course, to get positive 5. So this cubic has 3 real zeros. Okay. Down below, number 3, I actually continued in this particular instance where you can factor, very much like we did number 2 in the example up above. 4x is the GCF, and if you factor out or divide out the 4x, same thing, you're left with 3x squared plus 25. Still all equal to 0. It turns out that when you set this equal to 0, you get 1 real 0 of 0. And then this right here, when you set that equal to 0, subtract 25 divided by 3, you get negative 25 thirds. And then if you square root both sides, you'll end up with the square root of a negative number, which we know will have to have I in the result. The square root of 25 is 5. The square root of 3, well, in the denominator, you can't just leave it there, but the next step you see the rationalization. So plus or minus 5i over root 3, or 5 root 3i all over 3 as it's simplified. And then again, that's plus or minus. So in total, you have 1 real and 2 imaginaries, which makes sense again in context because it does in fact match the degree. Even though you won't see 2 imaginaries on the graph, they exist in the sense of total roots. You will see 1 real for sure on the graph. Okay. Now, this particular little breakdown of sorts here is me actually taking this 0. Let's say we graph this, right? We look at the graph of 12x cubed. We can do that actually quickly here. 12x cubed. And we see that 12x cubed plus 100x, when graphed, you should only see here, as it turns out, one x-intercept, because there is only one x-intercept. However, as it turns out, because this is a cubic, you should be able to kind of justify after you see that x-intercept via synthetic division, aka substitution. 0, of course, you plug in as such, so 12, there is no x squared. There is an x, and there is no just constant term. So we do our synthetic division, and our remainder, of course, is 0, as we expect it to be, because that's the y-coordinate. And then the resulting quotient is 12x squared plus 100. This particular equation, you can also subtract 100, divide by 12, and in the end, you'll still get these 2 imaginary zeros. So there's really more than one way, as we described in the last section, of course. There's more than one way to go through and factor your polynomials. On the next page, we'll continue again here, finding zeros. Complex conjugate theorem. Suppose a and b are real numbers with b not equal to 0. If a plus bi is a 0 of a polynomial function with real coefficients, then a minus bi is also a 0. So this speaks to the idea of conjugates, complex conjugates specifically. It does say for the next example to find all of the zeros of this quartic. I do recommend that you graph, so let's start this process by just that. Let's go ahead and graph. So we've got x to the 4th, and we've got minus 15x squared okay, and then we've got plus 38x, and if you front load your problems, minus 60, and if you front load your problems when you do that, you'll be able to see where in fact the function crosses the x-axis, if it even crosses the x-axis. So again, 1x to the 4th minus 15x squared plus 38x minus 60. So let's take a look, see what we have here. So here's our function. Okay, this is a cubic. Pardon, it's a quartic. It's a quartic because our degree, of course, is 4. Okay, now this function, as you can see, crosses the x-axis at this point, which is nice to be an integer value of -5, as is this. So -5 and 3 are distinct roots aka x-intercepts of your graph. So we're going to do synthetic division / substitution with just those two, -5 and 3, and see where that takes us. You could also test using other values. It turns out I wouldn't waste my time with those other values. It actually speaks to the Descartes rule of signs that we are not going to learn here. We're going to kind of skip that and just stick to the graph and the synthetic substitution and any other algebra from there, really, as we're about to see. So I did do, or at least I highlighted their approach where synthetic division on 3 does yield a remainder of 0. You can take these values, and in the depressed polynomial, we call it just below, you can see that the synthetic division does in fact continue as such. So you can do synthetic division on top of synthetic division. So again, these are the respective values of the quotient when you divide this into the original quartic. And then you repeat the process, except you do it, of course, with -5 as the graph again spoke to. So we started with 3, now we're working with -5, and if we continue the process, we get a remainder of 0, not surprisingly actually, but this right here specifically, yet again another depressed polynomial, x squared minus 2x plus 4. My synthetic division layered on top of one another is right here, so it's me just taking this on top of that. This is still something to work with. Turns out there are no more real zeros visible on the graph. There's literally only 2 synthetic divisions that can be done. However, we still know, thanks to the fundamental theorem of algebra, because it's a 4th degree, we're supposed to have 4 answers, and we only have 2. So there must be 2 additional zeros to solve for. And that's where you'll have to use extra algebra, and in this case, namely the quadratic formula. So the quadratic formula, x equals -b plus or minus the square root of b squared minus 4ac all over 2a. Your b value is -2, so there it is. Your a value is 1, so there it is, and here, and your c value is 4. Quadratic formula, if you do the math, and I know this is review, but please, you do need to check this, please. So you get what? 1 plus or minus I root 3. Double check your 2 imaginaries unfold as such. And I do recommend you put the I after root 3. Even though the answer key doesn't speak to that, it's good practice. So 1 plus or minus I root 3, or root 3I more specifically. So yeah, there are a total now of 4 answers to highlight. 2 reals, 3 and -5, which you again can see on the graph, and 2 imaginaries that you cannot. And again, these 2 imaginaries are technically conjugates of each other, as all conjugates unfold. They come out as conjugate pairs. All right, so there's a couple more problems to highlight. Number 1, if you do in fact do synthetic division after you've graphed, so I do recommend that we take a look at the graph here. Let's go ahead and take a look. All right, so we'll type in the problem, which again is x to the 3rd. And we've got plus x squared and plus 9x and plus 9. Okay, so we take a look at our function. It does cross the x-axis at only one point, so -1 is where I'll start my synthetic division. And I do that accordingly. We've got our coefficients of the original function. Add, multiply, and so on until, of course, not surprisingly, we get a remainder of 0. The remaining coefficients, of course, represent the quotient quadratic in this case, of which when you set it equal to 0, you subtract 9, so x squared equals -9, and square root both sides. When you square root both sides, you end up with x equals plus or minus 3i. That, of course, speaks to the final answer then as a total of answers. -1 is one real, and then plus or minus 3i as the imaginaries, for again a grand total of 3 thanks to the degree. The graph again only speaks to one real, but 2 imaginaries must be also part of your final solution set. What I will ask of you is to take a look at number 6 on your own. Graph it first. After you graph it, do synthetic division, as you can see here, twice. And then whatever remains, which will be this little bit, that in the end can be solved via simple just square rooting both sides. So this particular problem, double check and try it out on your own again. ends up having 4 answers thanks to the degree of 4.